It's maybe the biggest question you can ask. What happened before the beginning? What was there before everything we know, before the stars, before space, before time itself? What existed before the Big Bang? The simple, honest answer is that nobody knows for sure. And maybe we can't ever know. But that's a boring answer. It's the truth, but it's not the whole story. The real story is in the search for an answer. It's a journey to the very edge of what we can imagine. It pushes our science and our philosophy to their absolute limits. So let's talk about it. Let's talk about the ideas. Some are beautiful, some are strange. All of them try to peek behind the ultimate curtain. First, we have to get our heads around the Big Bang itself. Most people picture it as a giant explosion, like a bomb going off in the middle of a big, dark, empty room. But that's not quite right. And the difference is everything. When you ask about what came before, the Big Bang wasn't an explosion in space. It was the beginning of space. It was the beginning of time. It was the beginning of all the matter and energy we see today. Imagine a tiny, tiny dot, infinitely hot, infinitely dense. This dot contained everything. And then it started to expand, not like a firework expanding into the air. The dot itself, the very fabric of reality, started to stretch. Think of it like the surface of a balloon. Draw a bunch of dots on a deflated balloon. As you blow it up, all the dots move away from each other. Not because they are crawling across the balloon's surface, but because the surface itself is expanding. Every dot sees every other dot rushing away. That's our universe. The galaxies are the dots, and space itself is the balloon's skin that's still expanding today. This idea changes the question. If time itself began with the Big Bang, asking what came before the Big Bang is like asking what's north of the North Pole. The concept of north doesn't exist at the North Pole. It's the point where all the lines of longitude meet. It's a boundary of the system. In the same way, if time started at that moment, the word before might not have any meaning. It's a word we use to describe a sequence of events within time. But if you're at the start of time, there is no sequence yet. For a long time, this was the standard answer from many physicists. The question is meaningless. Stop asking. But humans are curious. We don't like being told not to ask. And more importantly, our science has gotten better. We've started to find cracks in that old wall. The wall is called the singularity. According to our best theory of gravity, Einstein's general relativity, if you rewind the expanding universe, everything crushes back down into that single point. It's a point of zero size and infinite density, the singularity. The problem is our laws of physics break down at a singularity. Math goes crazy, gives us nonsense answers. It's a sign that the theory is incomplete. General relativity is great for describing stars and galaxies, but it can't handle the very beginning. It's like trying to use a map of a city to understand what an atom is made of. You're using the wrong tool. To understand the origin of the universe, we need a theory that can combine gravity with the weird rules of the very small. We need a theory of quantum gravity. We don't have a complete one yet, but scientists are working on it, and their early ideas are what give us these fascinating possibilities for what came before. So let's explore those ideas. Let's step past the wall of the singularity and into the realm of speculation. One of the first major attempts to get around the meaningless question problem came from Stephen Hawking and his colleague James Hartle. They came up with something called the no-boundary proposal. It's a mind-bending idea. They used the math of quantum mechanics and suggested that as you go back toward the Big Bang, the nature of time changes. Think of it this way. We experience 3 dimensions of space, up, down, left, right, forward, backward, and 1 dimension of time, past, future. They flow differently. We can move around in space, but we are forced to move forward in time. Hawking and Hartle proposed that if you get close enough to the Big Bang, the dimension of time starts to behave just like another dimension of space. The distinction between time and space dissolves. What does that mean? It means there is no sharp starting point. There is no moment of creation. Imagine walking on the surface of the Earth. You can go south, but eventually you reach the South Pole. If someone asks you what's south of the South Pole, there's no answer. You can't go any more south. You've reached the boundary, but there isn't a spiky edge there. The surface is smooth and continuous. You can just turn around and start walking north again. The Hartle-Hawking model suggests the universe is like that. It's finite in the past, but it has no boundary, no starting edge, no moment of creation. The universe just is. It's a self-contained shape. So in this view, asking what came before the Big Bang is indeed a meaningless question, but not because time started there. It's meaningless because the whole concept of before disappears into a smooth geometric curve where time is just another direction. It's an elegant, if baffling, solution. It neatly closes the book. The universe didn't need a creator or cause, it simply exists, governed by the laws of physics. But not everyone was satisfied with this. Other physicists looked at the singularity and saw not an end, but a transition. This leads to another popular and very old idea, updated for modern physics, the cyclic universe. The idea that our universe is just one in a long, perhaps infinite, series of universes. This is the Big Bounce theory. It suggests that our Big Bang was not the beginning of everything, but the result of the collapse of a previous universe. Imagine a universe that expands for trillions of years. Eventually, its own gravity or some other force pulls it all back together. It rushes back in on itself faster and faster, heading for a big crunch. In the old version of this theory, the big crunch would just lead to a singularity, and that's the end of the story. But with ideas from quantum gravity, some physicists think that just before everything collapses into an infinitely dense point, some new quantum force would push back. A force of repulsion that becomes incredibly powerful at tiny scales. This force would stop the collapse and cause everything to bounce. So, the big crunch of a previous universe becomes the Big Bang of our universe. All the matter and energy from that old universe gets recycled and reshuffled, creating a new cosmos with its own stars and galaxies. In this model, our universe was born from the ashes of another, and our universe in the far distant future might itself collapse and give birth to the next one. It's an epic cycle of death and rebirth on a cosmic scale. There is no beginning. There is no end, just an endless cycle of expansion and contraction. The before to our Big Bang was another contracting universe. The question has a real physical answer. A modern version of this idea comes from string theory. String theory is an attempt to be the theory of everything. It says that the fundamental particles we see, like electrons and quarks, aren't points. They are tiny vibrating strings of energy, and string theory requires extra dimensions of space beyond the three we know. In a version of this called M-theory, our entire universe could exist on a giant membrane called a brane. Think of it like a huge flat sheet floating in a higher dimensional space, and this model imagines there isn't just one brane. There could be another parallel brane, another universe, floating nearby. Most of the time, these two universes just exist in parallel. But what if they were drawn together? What if they collided? The ekpyrotic model, as it's called, suggests that the Big Bang was exactly that. A collision between two branes in a higher dimension. The incredible energy released in that smash would create the hot, dense state of our universe and kick off its expansion. After the collision, the branes would drift apart, cool down, and form stars and galaxies. Then, after trillions of years, they might be pulled together again for another collision, another Big Bang, another new universe. So this is also a cyclic model, but instead of the universe collapsing on itself, the energy for the new beginning comes from an external event in a higher dimension. Before, the Big Bang was a cold, empty universe on a brane drifting toward another one. This sounds like pure science fiction, and right now, it is. There's no way to test it. But it's a mathematically consistent idea that comes out of one of our most promising, if unproven, physical theories. It opens our minds to the idea that our entire reality might just be a small part of a much larger, higher dimensional structure. Then there's an idea that is perhaps the most popular among cosmologists today. It's called eternal inflation, and it leads to the concept of the multiverse. We know that in its very first fraction of a second, the universe underwent an insane growth spurt called cosmic inflation. It expanded faster than the speed of light, smoothing out all the wrinkles and making the universe as big and uniform as it is today. We have very good evidence that this inflation happened. The theory of eternal inflation says that this process, once it starts, is very hard to stop. It might stop in some places. Our universe is one of those places, a little pocket where inflation stopped, allowing energy to turn into matter and form the cosmos we know. But outside our pocket, the inflation just keeps going, and going, and going, forever. Think of it like a pot of boiling water. The whole thing is bubbling furiously. That's the inflating space-time, the multiverse. Every now and then, a bubble forms in the water where the boiling stops for a moment. That bubble is a universe like ours, but the rest of the water keeps boiling, creating more and more bubbles. In this picture, our Big Bang wasn't the beginning of everything. It was just the moment our bubble formed. It was the moment inflation stopped in our little patch of reality. Before our Big Bang, there was just this eternally inflating chaotic space-time. And countless other Big Bangs were happening, creating countless other universes, or bubbles. This is the multiverse, an infinite ocean of eternally inflating space, constantly spawning new universes. Each of these universes could have different laws of physics. Some might be like ours. Others might be completely alien, with different forces or particles unable to support stars or life. So what existed before our Big Bang? A vast, pre-existing space-time that was already expanding at a mind-boggling rate. Our universe is just one tiny local event in a much grander, eternal cosmic drama. This idea is attractive because it doesn't require a single special beginning. The process is eternal, stretching infinitely into the past and future. It also helps explain a big mystery why the constants of our universe seem so perfectly fine-tuned for life. If you create an infinite number of universes, it's not surprising that at least one, by sheer chance, would end up with the right conditions for us to exist and ask these questions. We just happen to live in the lucky one. Finally, we come to the most philosophically challenging idea of all. Could the universe have come from nothing? When a physicist says nothing, they don't usually mean what a philosopher means. They don't mean the absolute absence of anything. No space, no time, no matter, no energy, no laws. That kind of nothing is very hard for science to deal with. Instead, a physicist's nothing is usually the quantum vacuum. And a quantum vacuum is not empty. It's a seething, bubbling soup of potential. Thanks to the uncertainty principle of quantum mechanics, energy can fluctuate. Particles can pop into existence from nothing and disappear again in a flash. These are called virtual particles. We know they exist. Their effects have been measured. So the idea goes like this. What if the entire universe is just a giant quantum fluctuation? A particle that popped into existence from the quantum vacuum, but on a cosmic scale. You might say, wait a minute, you can't just create a whole universe full of matter and energy out of nothing. That violates the law of conservation of energy. But there's a loophole. The universe has a neat feature. The total energy of the universe might actually be zero. Matter and radiation have positive energy. But gravity has negative energy. Every star, every galaxy is a source of positive energy, but it's also a source of gravity, which is a form of negative energy. It's possible that for the entire universe, the positive energy of all the stuff in it is perfectly balanced by the negative energy of all the gravity. If the total energy of the universe is zero, then you don't need any energy to create it. It's the ultimate free lunch. A quantum fluctuation could, in principle, create a universe from the vacuum without violating any laws of physics. In this scenario, before the Big Bang, there was nothing. The quantum vacuum. A state of potential, without space or time as we know it. Then, a random fluctuation occurred. A bubble of space-time popped into existence with its total energy at zero and immediately started inflating. Our universe was born. There may be no grand cycle, no other branes, no eternally inflating multiverse. Just a one-off event, a statistical fluke that happened once and created everything. So, where does this leave us? We have a handful of incredible ideas. One, the universe is self-contained. There is no before, because time itself peters out, like the lines of longitude at the South Pole. The universe simply is. Two, the universe is a cycle. Our Big Bang was a big bounce, the rebirth of a previous collapsed universe. Before was another universe dying. 3. The universe is a collision. Our Big Bang was the result of two branes smashing together in a higher dimension. Before was a cold, quiet reality waiting for impact. 4. The universe is a bubble. Our Big Bang was just one pocket of a much larger, eternally inflating multiverse. Before was this chaotic, ever-expanding metaspace. 5. The universe is a fluctuation. It popped into existence from the quantum vacuum with a total energy of zero. Before was the potential for existence, but not existence itself. None of these theories are proven. They are all speculative. They exist at the very frontier of theoretical physics, built from complex mathematics that is still being developed. We may never be able to test them directly. How do you see another universe? How do you get evidence from before time began? Maybe we can find indirect evidence. For example, some models of the Big Bounce or brane collisions predict specific subtle patterns in the faint afterglow of the Big Bang, the cosmic microwave background. Our telescopes are getting more and more sensitive. Perhaps one day we will see a faint ripple that points to a pre-Big Bang era. Maybe the way gravity waves behave could give us a clue. Scientists are actively looking for these signals. But for now, the question remains open. And maybe that's the point. The question forces us to be humble. It reminds us that our experience of reality, with its clear past, present, and future, might just be a local, temporary illusion. The true nature of existence could be far stranger and more grand than our minds can easily grasp. The search for an answer tells us more about ourselves than it does about the universe's origin. It shows our relentless curiosity, our refusal to accept we don't know as a final answer. We build incredible machines, we devise new forms of mathematics, we push our imaginations into impossible realms, all to answer this one simple question that a child might ask: what was there at the very beginning? We live our lives on a tiny planet, orbiting an average star in a quiet corner of one galaxy among billions. We are here for a cosmic blink of an eye, and yet, with our minds, we can try to reach back to the first moment of time. We can try to imagine a time before time. We can build stories, backed by mathematics, of bouncing universes and colliding branes and infinite multiverses. We don't have the answer. We only have these beautiful, strange, and powerful ideas. And for now, that has to be enough. The truth is still out there, hiding behind the glare of the Big Bang. And we will keep looking for it.